Hi all, welcome to the new session. So, in our previous sessions we learned moment of inertia, rigid body and definition of moment of inertia, and we learned moment of inertia of some regular shapes. So, in this session we are just going to find out the moment of inertia of rectangular lamina, similarly ring, circular disc, etc. So, first we are just going to find out what is the moment of inertia of a rectangular bar, uniform bar of rectangular cross section. In the previous sessions we learned moment of inertia of rectangular lamina. So, this is a uniform bar of rectangular cross section, and firstly we are finding the moment of inertia of this solid bar. You can see this one solid bar about an axis perpendicular to the length of the bar and passing through its center of mass. So, this is the axis passing through its center of mass and perpendicular to its length. Suppose this rectangular lamina is made up of rectangular bar is made up of a large number of rectangular lamina. So, here we are just considering that a rectangular bar of length L, breadth B and height h, and we are just imagine that the bar is made up of a large number of rectangular lamina. Consider one such lamina of mass small m. We have already discussed that the moment of inertia of a lamina about an axis perpendicular to its plane and passing through the center of mass, we have already discussed. It is given by m into L square plus B square by 12. Moment of inertia of a rectangular lamina is given by m into L square plus B square by 12. So, this is the moment of inertia of the rectangular lamina of mass smaller, and we are imagine that the solid bar is made up of a large number of such lamina. So, the moment of inertia of the whole bar about the axis y dash is nothing but the sum of moment of inertia of all such laminae, and it is given by this is the moment of inertia that we require I equal to what, sigma m into L square plus B square by 12, sigma m into L square plus B square by 12. So, L is constant, B is constant. So, sigma m, it is the total mass of the solid bar. So, it is nothing but the moment of inertia of the solid bar about an axis passing through its center of mass and perpendicular to its length is given by capital M into L square plus B square by 12. So, this is the moment of inertia of the solid bar or rectangular bar of cross section about an axis perpendicular to the length of the bar and passing through the center of mass. So, next we are just finding out moment of inertia of the same rectangular bar about an axis perpendicular to the length of the bar and passing through one of its corners. So, this is very important. So, here we are just going to find out the rectangular moment of inertia of this rectangular bar about an axis passing through one of its corners. So, about AG. So, this is very important. So, in the previous case we learned that the moment of inertia of the rectangular bar about an axis passing through its center of mass and perpendicular to its length about y dash is given by m into L square plus B square by 12. So, how we can calculate the moment of inertia of the rectangular bar about an axis passing through one of its corners? We can use parallel axis theorem. So, I equal to what, ICM plus product of mass and square of the distance between the axis. So, it is m into, so the distance between the axis, it is this one, let it be a be the distance between AG and y dash. We have to find out what is the distance A is nothing but AC dash. You can imagine a right angle triangle here. So, this is hypotenuse. So, here AF equal to L by 2, then C dash F equal to B by 2. So, what is A square? So, A square equal to what? L by 2 the whole square plus B by 2 the whole square. So, it is equal to L by 2 the whole square plus B by 2 the whole square. So, if you substitute, it is nothing but L square plus B square by 4. L square plus B square by 4. This is the distance between these two axes. Now, substitute the same A square in the first equation, this one, I equal to ICM plus MA square. So, this is the required moment of inertia, which is the moment of inertia of this rectangular bar about an axis which pass through one of its corners. I equal to ICM. ICM equal to M into L square plus B square by 12 plus M into A square. So, what is A square? L square plus B square by 4. M into L square plus B square by 4. So, take the LCM and then rearrange. So that you will get what? M into L square plus B square by 12 plus M into 3 L square plus what? 3 B square. So, if you solve the same, you will get I equal to M into L square plus B square by 3. I equal to M into L square plus B square by 3. So, this is the moment of inertia of the rectangular bar about an axis perpendicular to the length. So, this is perpendicular to the length and passing through one of its corners. So, here we need to learn two things, two formulae. First one about an axis passing through its center of mass and perpendicular to its length. It is given by M into L square plus B square by 12. So, this is very important. It is M into L square plus B square by 12. And second, if it passes through one of its corners and perpendicular to its length, use parallel axis theorem and you will get the moment of inertia as I equal to M into L square plus B square by 3. So, this is all about the moment of inertia of a rectangular bar. Next, we can discuss the moment of inertia of a circular ring. So, here also we are just considering about an axis passing through its center and perpendicular to its plane. So, we are just considering a circular ring of mass capital M and radius r. We need to find out the moment of inertia of the circular ring about AB. AB is nothing but it is an axis passing through its center and perpendicular to its plane. For that, we are just considering a small particle of mass m at the rim of the circular ring. Now, we are just finding out the moment of inertia of that particle. So, it is given by small m is the mass, m into distance, it is the radius of the ring, it is m into r square. And you know the ring is made up of a large number of such particles of mass small m. So, the moment of inertia of the ring about the axis AB is given by it is I equal to sigma m r square, which is nothing but sigma m is nothing but it is the total mass of the ring. It is given by capital M into r square. Okay. So, this is the moment of inertia of the ring about an axis passing through its center of mass and perpendicular to its plane. Next, we will consider the moment of inertia of the same ring of mass capital M and radius capital R about the diameter. So, for that we are considering the same ring of mass capital M and radius capital R about the diameter. So, since the ring is symmetrical about all the diameters, the moment of inertia about all the diameters are equal. So, moment of inertia of the ring about all diameters are equal. Here we are considering two such diameters AB and CD, two such diameters AB and CD, which are right angles, which are mutually perpendicular to each other, and we need to find out the moment of inertia of the ring about the diameter, one of the diameters. For this, we need to use the perpendicular axis theorem, because we know the moment of inertia of the same ring about an axis passing through its center and perpendicular to its plane, which is the moment of inertia of the ring about the perpendicular axis. We know what is that. It is given by capital M R square. Now, we can apply the perpendicular axis theorem here, because the other two axes AB and CD are mutually perpendicular to each other, and both intersect at the same point where the third perpendicular axis passes through. So, it is given by M R square equal to, let I be the moment of inertia about one of the diameters. So, it is equal to moment of inertia about AB, it is I, it is also moment of inertia about CD, that is also I, because the moment of inertia of the ring about all diameters are same. So, it is given by I plus I, which is given by M R square equal to 2I, or the moment of inertia of the ring about the diameter is given by I equal to M R square by 2. Okay. It is given by M R square by 2. So, you just consider this one, it is a moment of inertia about a perpendicular axis passing through the center of mass and perpendicular to its plane. It is given by M R square. Again, about the diameter, it is M R square by 2. Next, we will consider the moment of inertia of the same circular ring about a tangent lying in the plane of the ring. Okay. So, here also we are just considering a circular ring of mass capital M and radius capital R. Here CD be the axis which passes through that tangent, or it is about CD we need to find out the moment of inertia, because CD is a tangent. But we know AB, moment of inertia of the ring about AB, and AB is nothing but it is the moment of inertia about diameter. So, see, CD and AB are parallel to each other. We know the moment of inertia of the ring about AB, and we need to calculate the moment of inertia about CD. Which theorem will we use? We can use parallel axis theorem. So, let I be the moment of inertia of the ring about CD that we need to find out. So, I equal to, it is ICM plus mass of the body, it is capital M into, what is the distance between these two axes? This distance is nothing but the radius of the ring. So, it is capital M into capital R square. So, it is I equal to ICM plus M into capital R square. So, what is ICM? It is a moment of inertia about its diameter. So, ICM equal to M R square by 2. So, we have I equal to M R square by 2 plus M R square. M R square by 2 plus M R square, which is nothing but 3 by 2 M R square. 3 by 2 M R square. So, this is the moment of inertia of the circular ring about a tangent. It is given by 3 by 2 M R square. So, in this case, the case of the circular ring, we learned three formulae. First one, moment of inertia of the ring about an axis passing through its center and perpendicular to its plane, it is M R square. Second, we learned about its diameter, it is M R square by 2. Third, it is about a tangent, it is given by 3 by 2 M R square. So, we need to apply these formula as per the data of the questions. Do not use any of the formula. After seeing this moment of inertia of the ring, do not use mr square by 2 or mr square or mr square by 3 by 2 mr square. Just understand about which axis we need to find the moment of inertia. Okay. So, this is a very important thing, moment of inertia of a circular ring. So, next we will find out the moment of inertia of a circular disc. So, you can understand what is the difference between ring and disc. In the case of the disc, the mass is uniformly distributed of the surface. So, this is a disc and we are just considering the moment of inertia of this thin circular disc about an axis passing through its center and perpendicular to its plane. So, here we need to consider a circular disc of mass capital M and radius capital R. We are just considering a circular disc of mass capital M and radius capital R. Here also we are considering mass per unit area, which is given by sigma. Sigma equal to mass by area, this area equal to pi r square. So, sigma equal to m by pi r square, or the total mass of the body capital M equal to sigma into pi r square. So, we considered a circular disc of mass capital M and radius capital R, and sigma be the mass per unit area. So, finding out the moment of inertia of this circular disc about PQ, we are imagine that the disc is made up of a large number of concentric rings. Okay, the disc is made up of a large number of concentric rings. Consider one such ring. So, consider one such ring of thickness dx, which is at a distance of x from the axis. So, imagine the ring is a disc is made up of a large number of concentric rings. Consider one such ring of thickness dx and distance x. We have learned the moment of inertia of a ring about an axis perpendicular to its plane. For that, first we need to find out what is the mass of that ring. So, what is the area of that ring? First we need to find out what is the area of the ring. Area of the ring is given by, so this is the strip or this is the shape. Just cut that strip and stretch it out, so that it becomes a rectangle. It will take the shape of a rectangular bar. So, the area of that portion is nothing but length into breadth. So, that length is nothing but this circumference. So, what is the circumference of this ring? Its radius is x. So, the circumference is 2 pi x into width dx. So, 2 pi x dx be the area of that ring. So, you can easily find out what is the mass of that ring, because we know mass per unit area is sigma. So, mass of the ring is area of the ring, it is 2 pi x dx into sigma. So, this is the mass of the ring. Next, you can easily find out what is the moment of inertia of this particular ring, which is at a distance of x from the axis of rotation, which is given by I dash. Moment of inertia of the ring about an axis PQ, which is at a distance of x from the axis of rotation. It is given by what? Mass into distance square. So, the mass is 2 pi x dx sigma into what is the distance? It is x. So, into x square. So, we will get it is moment of inertia is nothing but 2 pi sigma x cube dx. Okay. So, this is the moment of inertia of the ring, which is at a distance of x from PQ, 2 pi sigma x cube dx. Now, what we need to do? We need to integrate this expression between the limit. So, the moment of inertia of the whole disc about the axis PQ is obtained by integrating this expression from 0 to R, from the center to the rim. So, from 0 to R. So, we are just going to finding out the moment of inertia of the disk about the axis PQ, and it is given by I equal to integral 0 to R 2 pi sigma x cube dx, 2 pi sigma x cube ds. So, 2 pi sigma you can take outside, 2 pi sigma integral x cube, it is x raised to 4 by 4 within limit 0 to R, within limit 0 to R. Apply the limits, you will get it is 2 pi sigma R raised to 4 by 4, R raised to 4 by 4. Here also we know the mass is given by, the mass of the disk is given by sigma pi r square. So, we need to group these terms, sigma pi r square here. So, sigma is there, pi r square. So, it is given by equal to sigma pi r square. What remains next? 2, 4 cancel out. So, it is r square by 2. So, sigma pi r square is the total mass of the disk. So, it is m r square by 2, m r square by 2, m r square by 2. So, this is the moment of inertia of the disk of mass capital M and radius capital R. So, in the starting part or in the first part of the session, I have discussed that the moment of inertia of the ring is more than the moment of inertia of the circular disk because of the distribution of mass from the axis. Here you can see moment of inertia of the disk is m r square by 2, whereas the moment of inertia of the ring is m r square. So, the moment of inertia, the disk and ring having the same mass, moment of inertia of the disk is smaller than the moment of inertia of the ring. So, this is m r square by 2. Next, we need to find out the moment of inertia of the disk about the diameter. We are using the same thing, same steps. We need to consider two diameters, and since the disk is symmetrical about the diameters, moment of inertia of the disk about all the diameters are same. So, we are considering two such diameters AB and CD, and we know the moment of inertia of the disk about PQ, which is the perpendicular axis, and we will use perpendicular axis theorem here. So, the moment of inertia of the disk about PQ, we know what is that? It is m r square by 2. It is m r square by 2, which is equal to, if I be the moment of inertia of the disk about diameter, it is given by I plus I, because the moment of inertia of the disk about all the diameters are same. So, it is m r square by 2 equal to I plus I, which is 2 I equal to m r square by 2, or we have I equal to m r square by 4, I equal to m r square by 4. So, this is the moment of inertia of the circular disk about the diameter. It is m r square by 4. So, here also we learned two formulae. First one, moment of inertia of the disk about an axis passing through its center and perpendicular to its plane, and it is given by m r square by 2, and also we have discussed moment of inertia of the same circular disk of mass capital M and radius r about its diameter, and it is given by m r square by 4. So, we learn moment of inertia of the ring as well as the moment of inertia of the circular disk. So, next we are going to discuss the moment of inertia of an annular disk. You know what is an annular disk? So, it is similar to circular disk, but a small portion has been removed from the center. So, this is the shape of an annular disk. Here also the treatment is same, the steps are same what we did in moment of inertia of a circular disk. So, First one, we need to find out the moment of inertia of an annular disc about an axis passing through the center and perpendicular to its plane. Here also we are considering an annular disc of mass capital M. Here you have two radius, it is inner radius r1 and outer radius r2. So, here we are just considering an annular disc of inner radius r1 and outer radius r2. Here also we are considering sigma, which is the mass per unit area, sigma equal to m by area of this annular disc. It is nothing but pi into r2 square minus r1 square, pi into r2 square minus r1 square, or the mass of this annular disc equal to sigma pi r2 square minus r1 square. So, we consider an annular disc of mass capital M, inner radius r1 and outer radius r2. Here also we are just imagine that the disc is made up of a large number of concentric rings, and we will find out the moment of inertia of one such ring about the axis. It is similar to what we have obtained in the previous case. So, here also the area of the ring is 2 pi x dx, the mass of the ring it is 2 pi x dx sigma, the same thing. The same thing we got in what? In the circular disc. So, this one, mass of the ring is 2 pi x dx sigma. Okay. So, here also we will get the same thing, the mass of the ring is 2 pi x dx sigma. So, the moment of inertia of the ring about the axis, it is given by moment of inertia of the ring about the axis PQ is given by, it is I dash, it is given by, it is the same formula what we have obtained in the previous case, it is 2 pi sigma x cube dx. This is what we obtained in the earlier case of circular disc also, 2 pi sigma x cube dx. So, the next step is different. In the case of circular disc, we integrated this expression from 0 to r. Here, if you want to obtain the moment of inertia of this annular disc about the axis PQ, you have to integrate the expression from r1 to r2. That is the only difference. You have to integrate the expression from r1 to r2. So, I equal to, so here I equal to integrate r1 to r2, 2 pi sigma x cube dx, 2 pi sigma x cube dx. Here also x raised to 4 by 4 and apply the limit r1 and r2. So, that you will get it is equal to 2 pi sigma by 4, it is nothing but r2 raised to 4 minus r1 raised to 4. It is 2 pi sigma by 4 r2 raised to 4 minus r1 raised to 4. So, 2 cancel, it will get it will give you pi sigma into r2 raised to 4 minus r1 raised to 4. So, here also you can make another thing. So, here the mass is what? The mass is sigma pi r2 square minus r1 square, sigma pi r2 square minus r1 square. So, we can write, we can rearrange this one as, we can rearrange this one as 2 by 4 cancel, it is pi sigma r2 raised to 4 minus r1 raised to 4, it is a square minus b square, it is a plus b into a minus b. So, it is r2 square minus r1 square into r2 square plus r1 square by 2. Okay. And the mass is nothing but, sigma pi r2 square minus r1 square. So, sigma pi r2 square minus r1 square. So, this is nothing but the total mass of the annular disc. So, the answer is moment of inertia is given by m into r1 square plus r2 square by 2. And so, this is the moment of inertia of the annular disc about an axis passing through its center and perpendicular to its plane. It is m into r1 square plus r2 square by 2. Similarly, you will get the moment of inertia of the same annular disc about the diameter. So, about the diameter, you know, it is I plus I. So, I plus I equal to, we can use the perpendicular axis theorem, I plus I equal to what? M into r1 square plus r2 square by 2. So, 2I and or moment of inertia of the annular disc about the diameter I equal to m into r1 square plus r2 square by 4. So, this is the moment of inertia of the annular disc about the diameter. So, here also we learn two formula, moment of inertia of the annular disc about an axis perpendicular to its plane and the moment of inertia of the annular disc about the diameter. So, with this I am just concluding this session, and we will see the moment of inertia of other shapes in our next session. Bye for now. Thank you.